Okay, so we're going to talk now about formulas for ionic compounds. So now that we know how ionic bonds form, now we're going to talk about how you write the formulas, and so that way you don't have to do out the dot diagrams and, you know, lose or gain the arrows and the electrons. It's actually a little bit easier way to do these. So first what we're talking about is exactly what a formula unit is, kind of a vocabulary term here. Okay, chemical formula for an ionic compound is called a formula unit. So it's kind of like a molecule, but for ionic compounds. We'll talk more about this later, but molecule is really kind of a term we kind of reserve for covalent bonds. We tend to deal with formula units as being what we talk about for an ionic bond, but all it means is it's the simplest ratio of your ions. Okay, so it's the simplest ratio of the ions. So if I have one Na for every Cl, then that would be the formula unit. I'd have one Na for every one Cl. If I would had to have, say for example, 2 chlorines for magnesium, so then I would have 1 magnesium for 2 chlorines. That's the formula unit for magnesium and chlorine, 1 to 2 versus 1 to 1. Okay, so it's a formula unit is kind of just how many are put together for an ionic bond. Okay, so first we're talking about here is monatomic ions, all right, and they are the same charge. Okay, if they're in the same group, why? Because they have the same number of valence electrons. Okay, let's remember that metals lose electrons and nonmetals gain electrons. So nonmetals gain electrons to be negative, and metals lose them to be positive. So let's look here at my elements and figure out, based on periodic table, what charges things are going to be. Alright, so remember that my group 1 here, okay, lithium, sodium, potassium all have the 1 valence electron. They have the 1 little dot by them. So that means they can lose 1. Well, if they want to lose 1 electron to be stable to be a noble gas, these are all 1 plus, okay, minus hydrogen. Okay, then beryllium had 2 valence electrons, so it wants to lose 2 electrons, so it's going to be a 2 plus. I'm going to skip the D block for a second. Okay, go to group 13, okay, or group 3A, depending on how you count it. Alright, these had 3 valence electrons, remember, so they got to lose 3 to go backwards to be a noble gas, so these are all 3 plus. Now you got to watch, because you get down here to the bottom, and some of these don't quite act like how you would want them to act, but for the most part we deal with a 3 plus. Boron tends to be more non-metal than metal, but that's kind of for later, alright? Now you would think that then these would be a 4 plus with the next one. Well, the thing is that you want to get to 8. So carbon, silicon, germanium, and tin, and lead can kind of either gain 4 or lose 4 depending on what they want to do. Well, so they're kind of a 4 plus or minus, alright? When you get down here to tin and lead, these ones are usually a 4 plus. Carbon and Si and Ge tend not to actually lose, but actually share. So we kind of skip those for right now, because that is kind of a dicey group. But like I said, tin and lead are definitely more metallic. They're kind of underneath the little thing that would go in here to talk about being a metalloid. So they're more transition metal-like, which means they're usually either 4 plus or actually 2 plus. Okay. Then we go back to the normal here. We look at ones that are 5. Well, nitrogen has 5 valence electrons, so it's going to want to gain 3 more. Alright, which means it's going to be a 3 negative. Oxygen's going to want to gain 2 more electrons to be 2 negative. Fluoride is 1 negative, and these are happy just the way they are. They already have our 8 electrons they want to have, so those are not a charge. So I could tell you right off the bat that O, S, Se, and Te are all pretty much going to be a 2 negative. We want to gain 2 electrons. So that's how we kind of always know what charges things are. It goes 1, 2, 3, with a space, 3, 2, 1. Okay, so we look at transition elements. Okay, these are charges that tend to change due to their D block being on a previous energy level. So we have a 4s and then a 3d, or a 5s and then a 4d, but the D's usually aren't full, so that's where it gets kind of dicey as to what you count as an electron, valence electron, and what you don't count. They're usually a 2 plus, sometimes they're 3, 4, 5, or 6. Like I said earlier, tin and lead are actually usually 4 or 2. Okay, so we'd have to tell you what the charge was. And what they normally, or how they write and tell you what the charge is they'll put tin. Okay, and it'll say tin, and they'll have a Roman numeral after it. And that Roman numeral is actually the charge. Okay, so you gotta know little Roman numerals, 1, 2, 3, 4, 5, that is 4. So that would mean that that tin is a 4 plus. If it was tin as it was 2, it would be like this, and that's tin, meaning that it's a 2 plus charge. Okay, so that's how they tell you what the charges for things are. The thing again to remember here, alright, is that there's a difference between an ion and an element. Okay, oxide, and they say this kind of weird ending, we'll talk more about this in names, But if you see an "ide" ending for a nonmetal, that's the ion when it has, or when it's become an ion, when it's gained electrons. If you see just oxygen, that's just the element. Alright, so if you see this "ide" ending, we're going to deal more with later, that's actually the ion. So there is a way to tell between an ion and the element. Alright, if they ever talk about an oxidation number, that's the same thing as a charge, it's just a different term for it. Alright, that's the number of electrons that are lost or gained to be stable. When we talk about how you write a formula for a binary ionic compound, it has to be cation and then anion. You always do the metal first and then the nonmetal. Your total charge has to be 0, and the number of ions that you use is equal to your subscript. So you write that as a subscript as to how many you actually use. And you should have done these your freshman year, so they should be pretty easy, I hope. Okay? So we're going to turn the formula for an ionic bond between sodium and sulfur. Alright, so sodium is Na, sulfur is S. That's the first thing we do, is we got to know what our symbols are. The next thing we do is look at our charge. Okay, well, Na is in group 1. Okay, it's right here. So that means I know that it's a 1+. So I would put a 1+ right next to it, or right up top for a second. Okay, and S, I go look at it, what's S? Well, S is over here. S then is in that group, so it's going to be a 2-. So I have a 1+ and a 2-. Well, those do not readily equal out. Okay, so I have to use more of one or the other to make them equal. Well, I would need more of the sodium to make it equal with the sulfur, because I have more negatives than I do positives, so I need more positives. Well, how many of those do I need? Well, I need 2 to make it 2+ and 2-. So what you would do is you would write that as Na2S, because I need 2 of those to equal out with my sulfur. Notice how we did not put charges here. Alright, once you use the charge, you usually will rewrite it, because I don't need the charge anymore. The charge doesn't change, it's just kind of extra crap. You really don't want to write it in there, so we kind of leave it be. Alright, I would rewrite it as Na2S. Alright, so let's go ahead and look at the next one. Alright, aluminum. Aluminum, if I look on my chart up top, my periodic table, okay, aluminum's right here. Aluminum is a 3+. Okay, oxygen is in that same group as sulfur, so oxygen's a 2-. Now I've got to get these to equal. Now how do I get these to equal? Well, if I add another oxygen, okay, so if I add another O, that's going to be another 2-. Well, now I'm good. I have 4 negatives. I got more negatives, but now I have 3 positive. So I had too many positives. Well, now I have too many negatives. So if I would add another aluminum, try and equal it out, well, now I've got 6+, because that ion is always that charge. You can't change the charge. Okay? So I have 6+ and 4 negative. So I need some more negatives. So I would add another negative, and now I've got 6 negative and 6 positive. So now I'm good. Okay, I had 2 aluminums and 3 oxygens, Al2O3. Alright, last one. The formula for palladium-2 and phosphorus. So palladium-2, it has something that's 2 because it's a D block element. Palladium's Pd. That way I know it's a 2+. Phosphorus is in group 15. Okay, and I look at my chart. Way up here. That's where that phosphorus is a 3-. Alright, so I gotta do this whole thing with my 3s and 2s again. Alright, I add another palladium, that's 4+, add another phosphorus, that's 6-. Add another palladium, that's 6+. So Pd, 3, P2. It's gonna write O there. Alright, what you kind of should notice from these two is that when you have charges of 2s and 3s, yeah, you use 2 and 3 of each one. You kind of always have the 6+ as the total. Okay. When we see our charges, okay, you can also look at it from what we call crossing a charge. Alright, you started out with a 2+ here, and I started out with a 3-. Well, notice how that's a 2 there, and notice how that's a 3 there. You kind of cross them. It always works that way. Because up here we had a 3+ and a 2-. The 3 went down there, the 2 went over there. It always works out like that. It's called the crossing a charge. Another kind of little shortcut.